Thank you very much. The short form of the title is Big Data for IT Operations. My name is Omer Trajman. I'm the CEO of Rokana. Just to give you sort of a brief background, I got started in big data at a company called Vertica, which is now part of HP. I ran the field team for Cloudera and spent a lot of this time over the past 10 years or so working with customers who are adopting a lot of the technologies that you've heard about today, really the precursors to those technologies, early columnar storage, early Hadoop and MapReduce, and some of the later systems. And discovered along the way that the challenges that people had were increasingly not how to adopt and build on the technologies. The ecosystem has evolved, the education has evolved, conferences such as Buzzwords have provided people with the tools to actually build. But actually taking these technologies and running them in data centers at scale for mission-critical deployments, that's where a lot of the people that I've worked with struggled. So it wasn't actually, say, installing Solar or Elastic or Hadoop, or even, if you look at Ted's talk just now about Drill, there's great tutorials about how to use it. It was when you wanted to run it globally. When you had 5 data centers and 2 of those are actually hosted cloud providers and you're actually trying to deploy these technologies, this is where we saw a lot of people struggling because these technologies are fundamentally new. They're distributed systems. They're built to recover from failures. They are shared services where multiple applications might be using the same technologies. And so a lot of this is what led to investigation that ended up leading us to found Rokana. I'm going to talk about the investigation. I'm going to talk a little bit about the background and the different areas we use to kind of inspire how we think about solving these problems. Before I jump into that, just to highlight a little bit about the evolution of IT. If you haven't been living in a data center, if you haven't been operating these systems, it's worth taking a step back to understand the context in which people run these technologies today. If you go way back 30 years when people were running minis, non-x86 systems, maybe they had to deal with tens of different systems, right? It was kind of a collection of different systems under management that you could write down on a piece of paper, you could put it on a big whiteboard, you could print it out and understand what things were going on. In the era of Web 1.0, we moved to x86 servers, and all of a sudden there were maybe hundreds of different systems. We named our servers after cities or planets, and you could still mentally map that in your head. There were specialized different servers, the web server, Web 1, maybe Web 2, maybe Web 3. That was kind of the extent of the system. And over the past decade, as virtualization has been introduced, we've now moved to a world where you maybe have thousands. And it's still an architecture map that you can reason about. You can search through different systems. The redundancies are still built in largely at the hardware layer, or in the case of virtualization, by being able to do, say, disaster recovery or vMotion. Over the past few years, certainly with the onset of Amazon Web Services and now Google Cloud Engine, with talking about, I'll go back to Ted's talk, Drill running at 1,000 nodes by GA, when you talk about Hadoop deployments in the 1,000 nodes, and that's one component of a system that's running in multiple data centers, we're now in the tens of hundreds of thousands. Right? And so you see this introduction and complexity. The number of nodes in the logical data center network is growing. And this is a log-based graph, right? Just so you can see the size of the bars. If we plot this linearly, this is where we are. We're at the hockey stick in terms of complexity of the data center. What this means is that whereas once you could fit the way systems work in your head, think a banking ATM network. You have your mainframe, you have your ATMs, the bank controls the entire system and they can map it out. Today, at least in the US, we have mobile check deposit. I could be flying on a plane over the Atlantic, take a picture of a check, and expect the same results. That check gets deposited in the bank. And yet there's now dozens of different systems. The bank isn't in control of half of them. It doesn't control the phone. It doesn't control the operating system. It doesn't control the mobile networks. And we're expecting the same kind of application, the same kinds of results. So the complexity has gone through the roof. And so when we started realizing these problems, myself and my co-founders, we started looking at what other systems, where else are people dealing with this level of complexity? And so we took a step back and said, do we see complexity in the world, and what techniques were used by those systems? And a few of them came to mind. The first is high-frequency trading. Are people here familiar with what goes on in the world of high-frequency trading? All right, so it used to be you'd have a bunch of people sitting around handing paper to each other, trying to negotiate trades. Today, all the trading is done by computers, and it can be queried by computers, which means I can write a computer system that goes to the trading platform and says, how many people are trying to trade a particular stock? In fact, I want to know how many people are trying to trade every stock in the world. And so now you have this enormous complexity of multiple time series systems that are clocking in multiple times per millisecond. And so we looked at what high-frequency traders are doing, and they're building systems that use not search-based systems. They're not looking through things manually. In fact, most traders today are not actually invoking particular trades. They're invoking trade algorithms. Right? They're algorithmically operating how their systems transact. And what they're using is a lot of columnar technology. They're actually applying big data technologies that allow them to store every single quote, every single trade, everything that happens historically, so they can develop an algorithm, a hypothesis about how they might be able to trade, and then go back in time and play it through history and say, would this have been successful over time? And so it's a much more analytical approach that then they get to decide on the fly, do they use one algorithm or another in order to effectively operate the system in which they're running, which is, in this case, trading stocks. The other one, which I'm sure you're all now well familiar with, is ad targeting. There's been talks today and at many conferences about how ad targeting systems work. I go to a web page, whether it's Google or another. There's a special space on the page that's reserved for hundreds of different companies to, within a few milliseconds as the page is rendering, collect a little bit of information about me and bid on whether they should actually be displaying an advertisement at that point in time. And so the real-time bidding systems, the advertising systems behind this, work in some ways similarly to the high-frequency trading systems, but the cost models and the cost dynamics are very different. They're not trading stocks, which are, relatively speaking, static in terms of this stock is for IBM, and I know that IBM is a known quantity. They're trading impressions over people whose interests and what you're particularly searching for changes over time. So now you have the same kinds of algorithms permuted to think about systems that are actually changing dynamically. And so when we look today at ephemeral systems, I have 1,000 web servers, but they burst to 5,000 web servers depending on traffic as maybe a front end for a gaming system. How people are using that system, how people are involved in that system, how those web servers scale and then contract and the profiles of them, those change. So there's some applicability that we can think of from HFT. There's some applicability that we can think of from ad targeting. And the other one, which is somewhat related, and if anyone's familiar with these systems, personalized recommender systems. You go to Amazon, you go to Facebook, it recommends certain things for you. And here, again, the cost model is different. They're not spending money anymore. It's a question of if I can fit one thing in one place based on the last few actions, what would that be? And here, there's algorithms that are designed much more around pattern matching. I want to take a model that I've developed and designed and fit that model or run that model at runtime, depending on the particular behaviors that are occurring. So we basically looked at a bunch of the algorithms, the technologies, the techniques that people were using to build these systems. And these systems are built on a lot of the things you've heard about today. They're built on Solr and Elastic. They're built on Hadoop and HBase and similar technologies. And we started thinking about how do you actually see these data points, right? If I'm not the user, not the person who's executing the trade, I'm not the person who's seeing the ad, I'm the analyst behind it. I actually need to run one of these systems, and I have billions of data points a day. So a classic charting system isn't going to work. I'm never going to see every single data point. I have thousands of attributes in each of these data points. I'm never going to be able to visualize every single facet. How do I permute my view of that data in a way to call up things that actually give me actionable viz? It's not just a pie chart and a line graph. There are very specific visualizations and very specific ways that people look at this data in order to understand it. And we've started thinking about how to apply those to IT. The first one we started thinking about, if you've ever seen Google Finance, it looks like this. At first blush, you look at it, you say, hey, that's a line graph. That's not very interesting. I've got 3 time series. So what? What becomes interesting is that they're not trying to mix different kinds of metrics, right? So they're basically trying to say, well, this is change not based on the absolute value of the stock. It's a percentage-based change. So when I look at 2 stock indices, they may not be aligned in terms of their absolute value. But if I'm trading stocks, the percentage change is what I actually care about. If I have $1,000 invested in one index versus another, the same percentage change should result in the same percentage gain or loss. So normalizing these time series is one way that this visualization, kind of in a very subtle fashion, is able to communicate a lot of data points concisely. The other that's interesting is these annotations. Right, so when I look at a time series graph, I kind of have to think about, well, what's actually going on? If I have a concrete event, and let's relate this back to data centers, I have a security intrusion product, or I have an anomaly detection algorithm, or I have an IT person running a ticket system who rebooted a server, and I'm looking at CPU metrics over time of 1,000 systems, and all of a sudden I see a drop in CPU and then a spike in CPU. Well, if someone rebooted that system, that's useful information to know. If I can plot that against the same graph, all of a sudden I don't go down a rabbit hole trying to investigate why a particular system rebooted. It becomes apparent for me. The other one that's really interesting, and you can plot 1,000 data points, you can plot 1 billion data points, is how you do directed graphs when there's circular aspects of the graph. When you have an application server, a web server, a database server, and a particular session involves 100 application server calls and 1,000 database server calls, maybe not a well-designed one, but right, let's say 10 app server and 100 database server calls, right, and that's happening 1 billion times over the course of the day. It's very hard to understand the nature of that system when you have elastic number of web servers, when you have round robining on your application servers, when your database server isn't an Oracle system, but it's Cassandra, right? And it's actually replicated and sharded across 3 data centers, right? That's kind of a modern application. Visualizing it using this method, and here we're just looking at, this is you know, traffic to the Rokana website, but visualizing it using a method where you actually have sort of these sort of directed data flow graphs where I'm not particularly saying one node is in one location. I have, you know, a career section here, a career section here, a career section there. People got to it from different ways. Allows me to understand where are the hotspots, where do things happen frequently, where are the anomalies, where are things that are happening a little more esoterically, and it's a visualization that scales. It allows me to look at 1 billion data points a day over 90 days, over 180 days, and I can still understand the same concepts behind it. The other one that we've been working on that's really, we found very useful and interesting is this idea of taking standard bar charts, or if you look at a normal histogram, but then breaking them out and stacking them. And you can stack them to look at different things. You can look at sort of different directions within the data set. You can